Hello and welcome to the second session on moment distribution method and myself Vahini M of GEC Haveri. Let us take the analysis of continuous beams without sinking. The first example on continuous beam is as shown in figure, which has to be analyzed by using moment distribution method so that we can draw shear force diagram, bending moment diagram and elastic curve. So the given problem is a continuous beam ABCD wherein support A and D are fixed. This is a fixed continuous beam. AB is subjected to a central point load of 50 kN, BC is subjected to UDL of 15 kN per meter and CD is subjected to an eccentric point load. So first step is to find the fixed end moments. Let us find the fixed end moment for MFAB. MFAB, since it is subjected to a central point load, the formula is minus WL by 8, where W is the magnitude of the point load, L is span of the beam AB member and then 8 divided by 8. Substitute the values of WL so that we can obtain the fixed end moment as minus 25 kilonewton meter. Next we have to find MFBA, fixed end moment for BA. So that is equal to plus WL by 8. That will be equal to, if you substitute the value of W and L, it will be equal to plus 25 kilonewton meter. Next we will find MFBC, fixed end moment for BC member. That is equal to, since it is subjected to a UDL, that is equal to minus WL square by 12, where W is equal to intensity of UDL 15 minus 15 into L is length of the member BC 5 square by 12, that is equal to minus 31.25 kilonewton meter. Next MFCB, that is calculated by using the relation WL square by 12. Substitute the values of W and L, you will be obtaining MFCB as plus 31.25 kilonewton meter. Next MFCD, since it is subjected to an eccentric point load, the formula to be applied is minus WAB square by L square, where W is the magnitude of the point load, A, small a is distance of the point load from the left end and B is distance of the point load from the right end and L is span of the member. Substitute those values. W 80, A is 2 meter, B is 3 meter and length is 5 meter. And if you calculate it, you are going to obtain it as minus 57.6 kilonewton meter. Next MFDC, fixed end moment from end DC, that is calculated by using WBA square by L square. WB is 3 meter and A is 2 meter. 80 into 3 into 2 square by 5 square, that will be equal to plus 38.4 kilonewton meter. That is the calculation of fixed end moments. Next step is to calculate the distribution factors, using which we have to distribute the moments applied at a joint and for the members which are meeting at that joint. So in the problem, B and C are the intermediate joints. So we can observe from the figure. So we have to calculate the distribution factors only for the intermediate joints. So B and C are the intermediate joints. So you can observe for joint B, we have got member BA and BC meeting at joint B. Okay, and the far end condition for member BA is fixed. When the far end is fixed, okay, so the relative stiffness will be I by L, and for BC member, since it is a continuous, so the relative stiffness will also be equal to I by L. Similarly, at end C, we have got two members meeting at joint C, that is CB and CD. So CB, again it is continuous, therefore the relative stiffness is I by L, and for CD member the far end is fixed, therefore the relative stiffness is also equal to I by L. So that calculations are made in the form of a table. So in the first row we will take the joints of the given beam. So in the first row, the joint, then the first column we will take the joints, in the second column the members meeting at that joint, and the third column we have relative stiffness, and in fourth column we have total stiffness, and then the fifth column is distribution factor, which is calculated by the ratio of K divided by sigma K. So now we will take up the individual intermediate joints. So let us first consider joint B. So the members meeting at joint B are BA and BC. So first we will calculate the relative stiffness for member BA. So since the far end A is fixed, relative stiffness is calculated by using the relation I by L. So since there is no mention of the variation of I, so we will assume it as 1I. So I divided by 4. Length of the member is 4. If you calculate it, it will be equal to 0.25 I. Next, the member meeting at joint B is BC. Again, it's a continuous member. Therefore, the relative stiffness is I by L. So the length of the member is 5 and I is 1I. So if you calculate it, it will be 0.2 I. So the total stiffness is nothing but the summation of relative stiffnesses of all the members meeting at a joint. So in this, total stiffness is the summation of relative stiffness for member BA as well as relative stiffness for member BC. So therefore, summation of 0.25 plus 0.2 will lead to 0.45 I. And now we have to calculate the distribution factor for BA and BC. So distribution factor is calculated by using K divided by sigma K, relative stiffness of a member to the total stiffness of the joint. Okay. So for distribution factor for BA is equal to KBA divided by sigma K. KBA is 0.25 I divided by 0.45 I. I will get cancelled and therefore the distribution factor is 0.56. And then distribution factor for BC member will be equal to the ratio of relative stiffness for member BC to the total stiffness. So the relative stiffness for member BC is 0.2 I to the total stiffness is 0.45 I. Therefore the distribution factor is 0.44. Next we will consider the other intermediate joint, that is joint C. So the members meeting at joint C are CB and CD. So first we will consider member CB. The relative stiffness for member CB is I by L. It is also equal to I by 5, which will be equal to 0.2 I. Next, the member CD is calculated. Relative stiffness for member CD is calculated by using I by L. The value of length is 5 meter. Therefore, the relative stiffness for member CD is also equal to 0.2 I. So the total stiffness at joint C will be equal to the stiffness of member CB plus stiffness of member CD. That will be equal to 0.4 I. So the distribution factor is ratio of relative stiffness of member CB to total stiffness. That will be equal to 0.5. And then relative stiffness for member CD to total stiffness will give the distribution factor for member CD. So if you observe these values, if you add the distribution factors at a joint, it will be always equal to 1. Okay, so 0.56 plus 0.44, that will be equal to 1, and 0.5 plus 0.5, that will be also equal to 1. It will be neither less than 1 nor more than 1. So it will be always equal to 1. So the next step is to distribute the moments, that is moment distribution. So that distribution is also made in the form of a table. So in the first row we have joint. So we will be placing all the joints in the structure. So we have got 4 joints A, B, C and D. Next we have next row. In the next row we have got member. So members coming under each joint are written in the second row. So under A joint we have got member AB, And under B we have got BA as well as BC. Next under C we have got member CB and CD, and then under joint D we have member DC. Next row we have to write the distribution factors for each member. So we have got distribution factors only for BA, BC and CB, CD. Therefore, we will not be writing any distribution value for AB as well as DC. So next, for BA it is 0.56, for BC 0.44, and then for CB it is 0.5, and then for CD again it is 0.5, and then for DC we don't have any values. So next, in the next row we have to write the fixed end moments. We have calculated it in the first step. So those values are to be entered in each box. So under AB we have got fixed end moment for AB is minus 25, and for BA it is plus 25, and then for BC it is minus 31.25, and for CB it is plus 31.25, and for CD minus 57.6, and then for DC it is plus 38.4. So next comes the balancing. So we have to balance each and every intermediate joints. So if we know that for the equilibrium or summation of moments at any intermediate joints should be equal to 0. So now we will take the joint B. If we add 25 minus 31.25, it is not equal to 0. So therefore it is imbalanced by 25 minus 31.25. So it is imbalanced by minus 6.25 kilonewton meter. So we have to balance this joint by applying plus 6.25, so that the net moment at joint B will be equal to 0. So as soon as we apply plus 6.25, that applied moment will be distributed according to the distribution factor. So plus 6.25 into 0.56 will be equal to 3.5, and plus 6.25 into 0.44 will be equal to 2.75. If you add these two, you will get plus 6.25, and if you add these two, you will get minus 6.25. Then if you add all these, you will get 0. Okay. So therefore, the difference between the fixed end moments has to be balanced by applying a moment in the opposite direction of same magnitude. Okay. So that moment has to be distributed among the members meeting at the joint according to the distribution factors. So in this case, minus 6.25 is the imbalancing moment. So that moment has to be distributed or balanced according to the distribution factors. So by applying a plus 6.25, so balancing moment will be equal to plus 6.25. So plus 6.25 into distribution factors. 6.25 into 0.56 is equal to 3.5, and 6.25 into 0.44 will be equal to 2.75. So next, the imbalancing moment at joint C is plus 31.25 minus 57.6. So if you add sigma MC, so we know that summation of moments at joint C should be equal to 0. So when we add the moments at joint C, we are obtaining a moment of minus 26.25 kilonewton meter. So that is the imbalancing moment. So imbalancing moment at joint C is minus 26.35. So what is the balancing moment then? Plus 26.35. Okay, so we have to apply a moment of plus 26.35 at joint C, and that moment will be distributed among CB and CD according to the distribution factors. Since the distribution factor is 0.5, so both will have an equal share. So 26.35 into 0.5 will be equal to 13.175 for CB as well as CD. That is the balancing of the fixed end moments. Okay, so now we have balanced the imbalancing moments at joint B as well as joint C. Okay, so by applying a moment of 26.35 at joint C and 6.25 at joint B, we have balanced the beam. But as soon as we apply a moment, okay, so some part of the moment will be carried to the far end depending upon the boundary conditions. So that moments we have already discussed, and and it is called as carry over moment. So we have to calculate in the next row, we have to calculate the carry over moments. So from BA to, we have applied a moment at joint B. So for member BA, AB will be the far end, and for member BC, CB will be the far end. Okay. So from BA to AB, so when you apply a moment of 6.25 at joint B, from member BA, half of the moment will be carried to the far end since end A is fixed. So half of this moment from BA to AB, it will be carried to AB. So half of 3.5 is 1.75. So that moment will be carried by the member AB due to the application of 6.25 kilonewton meter at joint B. For member BA, we have AB as the far end. So as soon as you apply 3.5, okay, so that is the moment shared by distributed by member BA. So half of this moment will be carried by the member AB. So next, for member BC, CB will be the far end. So half of this moment will be carried by member CB. So half of 2.75 is 1.375. In the same fashion, we have applied 26.35 kilonewton at joint C. So that moment is distributed among the member CB and CD. So this moment will induce the carryover moment at the far ends. So for CB member, BC will be the far end, and for CD member, DC will be the far end. So from CB member, half of this will be carried to the far end. So half of 13.175 is carried to the far end BC, 6.587. Similarly, for CD member, half of 13.175 is 6.587, that will be carried to the far end DC. This is carry over calculations. Okay. Next, again, as soon as the joints get carried by the moments, this joint becomes again imbalanced. So now if you can see, we are not getting at 0. It is imbalanced by 6.587. The joint B is imbalanced by 6.587, and similarly joint C is imbalanced by 1.375. So what we have to do? We have to again carry out the balancing. So the next step is balancing. So what is the imbalancing moment? 6.587. What should be the balancing moment then? We have to apply, so that we can make it 0, we have to apply minus 6.587 at joint B. So minus 6.587 into 0.6 will be equal to minus 3.688. Similarly, minus 6.587 into 0.44 will be equal to minus 2.898. So at joint C, the imbalancing moment is 1.375. So the balancing moment will be minus 1.375. So minus 1.375 is distributed among the members according to the distribution factor. So minus 1.375 into 0.5, that will be equal to minus 0.687. So minus 0.687 for both CB as well as CD. Again, this carry over and balancing will be repeated. So the next step is carry over. As soon as we have applied minus 6.587, so half of that moment will be, and that means some portion of that this moment will be carried to the far ends. Okay. So for member BA, the far end is AB. So half of this, my half of minus 3.688 will be equal to minus 1.844. This is a carryover moment at AB. Next, from BC to CB. So carryover moment will be from BC to CB. Half of minus 2.898 will be equal to minus 1.449. Next, from CB to BC, minus 0.687, half of which will be equal to minus 0.343. Next, from CD to DC, minus 0.687, half of this value will be minus 0.343. So that is the carryover of the calculations. Next, again, now the joint B and C are imbalanced. So again, the next step is balancing. So imbalancing moment is minus 0.343. Therefore, balancing moment will be plus 0.343. So plus 0.343 into distribution factor. Okay, plus 0.343 into 0.56 will be equal to 0.192. And then plus 0.343 into 0.44 will be equal to 0.151. Next, imbalancing moment at C is minus 0.1449. So the balancing moment will be plus 1.449. Okay. So the balancing moment 1.449 is distributed according to the distribution factors. 1.449 into 0.5 will be equal to 0.724. So that is the balancing. Again, the next step is carry over. So you can observe these values are decreasing. So initially it was 3 and 2 and it was 13 and later it has reduced to 6 and 1 and 1 point something, and now again it is 3, 2 and 0.6. So you can observe the values are reducing. So that means till how much we have to continue these cycles means so that these distributing moments or distribution moments are get negligible. So till then we have to carry the cycles. So the next step is carry over from BA to AB. Half of 1.192 is equal to 0.096, and from BC to CB, half of 0.151 is equal to 0.075. Next, from CB to BC, half of 0.724 is 0.362. Similarly, from CD to DC, 0.724 is 0.362. So that is the distribution of moments. So we will carry the same to the next page so that we can calculate the final moments. So the last column I have taken 0.096, 0.362, 0.075 and 0.362. So that is the carryover moments. You cannot stop after carryover. You have to stop only after balancing, because now the joint B and C are imbalanced. If you add the values, you will not get a balanced joint. Therefore, the next step is to balance joint B and C. So the imbalancing moment at joint B is 0.362. Therefore, the balancing moment will be minus 0.362. Minus 0.362 into 0.56 will be equal to minus 0.202, and minus 0.362 into 0.44 will be equal to minus 0.159. Next, the joint C is imbalanced by 0.075. So the balancing moment will be minus 0.075. So minus 0.075 into 0.5 will be equal to minus 0.037. It is both for CB as well as CD. So now the next step is to calculate the final moments. So the final moments are calculated by adding all these distributed moments and the fixed end moments from the fixed end moments. So till this, these are not, you cannot add distribution factors. So you have to add all these values: minus 25 plus 1.75 minus 1.844 plus 0.096. So that will be equal to minus 25. Similarly, you have to add all the fixed end moment from fixed end moment you have to add all the values, all the distributed moment values, fixed end moment plus distributed moment values under each column. Okay, so for member AB we have obtained the final moment as minus 25, and for member BC it is 24.8, and for BA it is 24.8, and for BC it is minus 24.8. Now you can observe the summation of moments at joint B is 0. Next, under C, if you add all the values, the moment at member CB is 44.42, and for CD it is minus 44.47. So the difference is very less, 0.05. Okay, so that is permitted. That difference is because of the rounding up errors. Okay, so next for member DC it is 45. So next step is to calculate the support reactions. So the support reactions are calculated by considering each span separately. So first let us consider AB span. AB span is considered with the end moment. So we have calculated MAB as plus 25 and MAB as minus 25 and MBA as 24.8 plus. So the sign convention is plus means clockwise moments and minus means anti-clockwise moments with the applied loading. So 50 kilonewton. Okay. So let us consider reaction at A as VA and reaction at B as VB1. Okay. So since at end A we have got fixed end, HA is the horizontal reaction. So let us apply the three equilibrium conditions. So first one is sigma Fx is equal to 0, which implies HA is equal to 0. Since there is no inclined or any horizontal loading, so HA will be equal to 0. Next, apply sigma Fy is equal to 0. Summation of forces in y direction is equal to 0. That implies VA plus VB1 is equal to 50 kilonewton. Next, we will apply the third condition, that is sigma MA is equal to 0. So the sign convention what we follow is clockwise moments are taken positive. So therefore the equation will be minus, because it is inducing anti-clockwise moment at A. So minus VB1 into length is 4 meter plus 50 into 2. Okay, and then minus 25, this end moment minus 25 plus 24.8, that is equal to 0. So which implies VB1 is equal to 24.95 kilonewton. Hence VA will be equal to 25.05 kilonewton. That is the calculation of reaction for member AB. Next we will calculate reactions for member BC. So BC is subjected to UDL of 15 kilonewton per meter. End moment at B is minus 24.8, that is MBC. Okay, and MCB is equal to plus 44.42. Apply the equilibrium conditions. Sigma Fy is equal to 0, which implies VB2 plus VC1 is equal to 15 into 5, that is equal to 75 kilonewton. Next you take sigma MB is equal to 0, which implies minus VC1 into 5 plus 15 into 5 into 2.5. Okay, so half W into L into L by 2. Okay, plus 44.42 minus 24.8, that is equal to 0, which implies VC1 is equal to 41.42 kilonewton. Next VB2 is equal to, therefore VB2 will be equal to 33.58 kilonewton. Therefore RB, reaction at B, is equal to summation of VB1 plus VB2, where VB1 is the reaction at B for member AB and VB2 is reaction at B for member BC. So VB1 is 24.95 plus 33.58 is equal to 58.53 kilonewton. Next we will consider member CD. So CD is with the end moments. At C we have got minus 44.42 and at D it is 45. So apply sigma fx is equal to 0, hd is equal to 0, there is no horizontal or inclined loading. Next apply sigma fy is equal to 0, which implies Vc2 plus Rd is equal to 80 kilonewton. Next sigma mc is equal to 0, that implies minus Rd into 5 plus 80 into 2 minus 44.42 plus 45, that is equal to 0. That implies Rd is equal to 32.1 kilonewton, and then Vc2 is equal to 47.9 kilonewton. Therefore, Rc, reaction at C, is equal to summation of Vc1 plus Vc2. Vc1 is reaction at C for member BC and Vc2 is reaction at C for member CD. So that is equal to 41.42 plus 47.9, that will be equal to 89.32 kilonewton. Next we have to draw shear force diagram. So to draw the shear force diagram, first we will write the given loading diagram with the reactions. So reaction at A is 25.5, reaction at B is 58.53 and reaction at C is 89.32 and reaction at D is 32.1 kilonewton. So to draw the shear force diagram, we have to draw the baseline, okay, of the same length as that of the given beam. So above the baseline we are going to draw the positive shear forces and below the baseline we have to draw the negative shear forces, okay. So left of A, we will start from left to right, okay. So shear force to the left of A is 0. Next shear force to the right of A, we have got a upward force of 25.05. So upward means positive shear force, so we will draw a line above the baseline for 25.05 kilonewton. Next shear force to, let us take this as E. So shear force to the left of E, so since there is no loading in between A and E, so it will be constant. So that is 25.05 and it will be constant till left of E. Next shear force to the right of E, so 25.05 minus 50, we have a downward force here, so 25.05 minus 50 will be equal to minus 24.95. So we have to draw a line in the downward direction till minus 24.95, and then from the right of E to the left of B we don't have any loading, therefore the shear force variation will be constant. Next at right of B we have a positive or upward force of 58.53 kilonewton. So we will add minus 24.93 plus 58.53, sorry, minus 24.95 plus 58.53, that will be equal to plus 33.58. So you have to draw a line in the upward. So plus 33 means this magnitude should be 35, this reference line will be 0, okay, plus 33.58. So from right of B to the left of C we have a UDL, okay. So we have to deduct that one. UDL will be acting in the downward direction. So plus 33.58 minus 15 into 5, that will be equal to minus 41.45. So you have to join a linearly varying line from plus 33.58 to minus 41.42. So that is the shear force to the left of C. Next right of C, so that will be equal to minus 41.42 plus 89.32. So that will be equal to plus 47.9, okay. So shear force to the right of C is plus 47.9. Next if you take this as F, shear force to the left of F, we don't have any loading in between C and F, just to the left of F, therefore the variation will be constant. And then shear force to the right of F, we have a downward force of 80 kilonewton. So therefore plus 47.9 minus 80 will be equal to minus 20.57. So draw a line such that you will get an ordinate of 20.57 in the downward direction. So next, from right of F to the left of left of D, we don't have any forces, therefore shear force variation will be constant, and then shear force to the right of D will be equal to minus 20.57 plus 32.1. I think we have made a mistake. I think there is a mistake here in this value, so please check this one. So that is the shear force diagram. Next is to draw the bending moment and elastic curve. So to draw bending moment and elastic curve, draw the reference loading diagram. Okay, and to draw the bending moment diagram, first we have to draw the end moments for each member like this. Okay, end moments for each member like this. MAB is minus 25, MBA is plus 24.8, MBC is minus 24.8, and MCB is plus 44.42, MCD is minus 44.42, and MDC is plus 45. Okay, so we have to use thumb rules to draw the support moment diagram. So to draw the support moment diagram, we will draw a reference line. Okay, so this baseline should be of same length as that of the given B. Okay, use the thumb rule such that, so for the left end use left hand thumb direction, and for the right end use the right hand thumb direction. Okay, so for left end, for MAB, the thumb direction is in the upward direction, so mark a line above the baseline for 25 kilonewton meter. Next, at right end we have a clockwise moment, so which shows that the right thumb is moving again in the upward direction, so mark a line for 24.8 kilonewton meter. So now we have to join these two with straight line. Okay, next again for member BC, use the same rule for left end left thumb and for right end right thumb. So the left thumb at BC, again it is showing in the upward direction, so the same value, same point can be taken, and for right end C, again the thumb is moving in the upward direction, so mark a line of 44.42 magnitude. Okay, so for C it is 44.42 and at B it is 24.8. Next at D, again see left thumb in the upward direction, and at D right thumb in the upward direction, so mark a line for 45 kilonewton meter. So now you join these two. So this is the magnitude of MDC, 45 kilonewton meter. So this is the support moment diagram, over which we have to superimpose with the free bending moment diagram. Okay, so free bending moment diagram, so treat individual beams as a simply supported beam. Okay, so simply supported beam with a central point load, so the variation of bending moment is a triangle. What is the maximum ordinate? That is equal to WL by 4, and it will be equal to minus 50. 50 is W, length is 4 meter, again divided by 4, therefore the magnitude of positive bending moment is 50 kilonewton meter. Next, for member BC we have UDL. So simply supported beam subjected to UDL throughout. What is the variation? It's a parabola. So what is the highest ordinate? It is equal to WL square by 8. So if you substitute the values of W as 15 and L as 5, it will be equal to 46.87 kilonewton meter. Next, for CD member, it is subjected to an eccentric point load. So in that case, the variation of bending moment is also a triangle, but the highest ordinate will be under the point load. So the magnitude of which is calculated by using WAB by L, where W is load magnitude, A is distance of load from left end, B is distance of load from the right end. So W is 80, A is 2, B is 3 and L is 5. So if you substitute it, you are going to get WAB by L as 96 kilonewton meter. So this is the free bending moment diagram, which are always positive, okay, and support moment diagrams are always negative, okay. So when we superimpose these two, the points where these two overlap or cross each other, they are at that point the bending moment will be 0. What we call those points as? We call those points as points of contraflexure, where the bending moment is 0, okay. So positive bending moment, negative bending moment, if you overlap it, the points where the bending moments are 0, those points are called as points of contraflexure. So this upper portion is net positive bending moment and this one is the net negative bending moment. So the supports are always subjected to negative moments and mid spans are always subjected to positive bending moment. Therefore, the reinforcements are provided at the bottom in the middle section of the beam and at the top in the end sections of the beam, okay. So that is the bending moment diagram. So next we have to plot the elastic curve. So to draw the elastic curve, we have to write the given beam without loading, okay. So take the beam without loading and the variation of elastic curve will be as that of the bending moment diagram. So we know that negative means hogging, that means the bending beam will hog in the upward direction, and positive means the beam will sag in the downward direction. So we can see that at these points the bending moment is 0, means deflection will be also 0, okay. So at these points the curve will cross the direction, okay. So at negative means hogging in the upward direction, positive means sagging in the downward direction. So if you write that, this is the variation of shear force diagram. So under positive it is sagging, under negative it is hogging in the upward, and for positive bending moment it is sagging in the downward direction. So this is the elastic curve. So that is how we can solve a problem fixed continuous beam using a moment distribution method. Thank you.